Tonight on Bang Goes the Theory, Jem is investigating the latest in wave technology.
Hey! I'm getting light! I'm getting light from waves!
Jan is larking about with ping pong balls.
Please! It seems like there's something holding it back.
And I'm going to demonstrate the theory of evolution using an eye and a very brainy man.
Reason tells me it would be easy for it to have evolved by natural selection.
That's Bang Goes the Theory, putting science to the test.
Hello and welcome to the show. First up, something that is as British as queuing at Wimbledon or the Queen's speech on Christmas Day, and that is talking about the weather. Now, nothing run-of-the-mill for me. I'm going to go back in time to find out where our weather came from in the first place. So here we are on the south coast, and it's early September, and it's warmish. But obviously in a couple of months we're going to be wondering whether or not it's going to be a white Christmas. But what actually causes the seasons? How can we get the nice warm weather in the summer and the cold, horrible weather in the winter? Well, the answer to that question is 4.6 billion years old. So come with me to the very dawn of the solar system. We're going to travel back in time to when the sun was just a few million years old and the planets were just being formed from a great swirling cloud of protoplanetary dust. So this is the new young sun, and behind me over there, that's the brand new Earth. Now, it's not a very nice place to be. You wouldn't really want to hang out on it. There's no atmosphere, no land masses, no oceans, nothing like that. Essentially, it's just a big lump of hot, soft rock, and the planets are still forming from all this rubble that's orbiting around our brand new sun. Huge asteroids hitting the Earth are a pretty rare phenomenon today, but back then it was happening all the time. The effect was that the Earth was knocked this way and that on its axis. So rather than it being a nice stable spinning top like this, the Earth's axis would have been wobbling all over the place like this. Now, you may be wondering, well, what's that got to do with the seasons? Well, ultimately, the seasons are determined by the angle at which the Earth is facing the sun. Even though the Earth's orbit is elliptical, meaning it's closest to the sun in January and furthest away in July, that makes very little difference to the amount of solar energy we receive. To show you how the tilt of the Earth affects the seasons, let's do an experiment. Right, let's imagine that the Earth's axis is flat on, parallel with the sun's, as it orbits round. That means all the sun's energy is going to be hitting the same bits of the Earth all the time throughout the year, and therefore you're not going to have any seasons. So the northern bits and the southern bits are going to be very dark and very cold. The equator, on the other hand, is going to be incredibly hot all the time. But the Earth is not at 90 degrees to the sun, it's at an angle. And that's all thanks to one massive collision. About 4.6 billion years ago, we had a next-door neighbour. A still-forming planet called Theia, just a bit smaller than the planet Mars. Unfortunately, its orbit became unstable, and one fateful day, it collided with the Earth. But this was no ordinary collision like the one that famously wiped out the dinosaurs. The energy from this collision was so huge that it actually blew out a portion of the Earth's crust into space and helped form our very large moon. And it's this 4.5 billion year old rock that seems to hold the key to making our planet such a nice place to live. The beauty of having a large moon is that it keeps the Earth very stable on its axis, tilted towards the sun at a perfect 23.5 degrees. So thanks to our moon, the Earth hardly wobbles at all. Over eons, the seasons have remained incredibly stable, the distribution of the sun's energy moving only slightly to the north or south over a 6-monthly cycle. Okay, so here we are. It's late summer, early autumn, and you can see the tilt of the Earth, which means most of the heat of the sun is aimed at the northern hemisphere, so we're all nice and warm-ish, and they're all freezing cold down here. Cut to 6 months later, the tilt remains exactly the same, but now it's the southern hemisphere that's basking in the sun's warmth. We're all freezing cold up here, wishing we were down there throwing prawns on the Barbie. So there you go. Basically, all you need to know, Liz, is that size does matter, because we've got this abnormally large moon compared to the size of the Earth. And its motion around the Earth and its gravitational influence means that we're not sort of wobbling.
Very good. If we were tilting on a wobbly axis, of course, we'd have serious extremes of weather in any one place. So we'd go from really hot desert to really, really cold Arctic conditions in a relatively short space of time, which would pose serious problems for all life forms on Earth.
I mean, like booking a summer holiday would be practically impossible.
No, it would be impossible, because we wouldn't be here to book one.
That'd be worse than I thought. Thing is, even with our relatively benign weather, it's still the biggest source of renewable energy we've got. But even though we've pretty much got solar power, we've got wind power, we have not cracked wave power. So I've been to Scotland to see what the latest scheme is.
As an island, the UK has an awful lot of coastline. This means that waves are usually here in abundance, and waves contain a surprising amount of power.
Even tiny little waves like these will easily lift a boat that it would normally take a forklift truck to move.
So where does this power come from? You can think of waves as solar power third hand. The sun heats the earth, making winds, and winds create the waves. It may sound inefficient, but the process effectively concentrates the energy. These boats weigh a few 100 tons each, and they're being thrown around like matchsticks. This makes me wonder, how much power is in a wave? The best way to find out is to get stuck in.
Although there's quite obviously not enough force in these waves for a bloke to surf, how much power is there in them? Well, there's a good rule of thumb for calculating it. It's half the height of the wave squared multiplied by the time between waves. So even little tiddlers like this have about 300 watts of power per metre, which means every metre of this coastline could be running your fridge.
And on our Atlantic coast, where the waves are generally bigger, each metre of coastline is on average buffeted by 40,000 watts of power. But the difficult thing is how to extract that power. The basic principle of most wave power systems is very simple. Use the motion of the wave to spin a turbine, which spins a dynamo, creating electricity.
This is a pretty neat way of getting electrical power out of waves. It's called an oscillating water column, or a dustbin with a fan on it, in layman's terms. Now what happens is, as the wave comes in, it rushes up the inside of the dustbin, squashing the air inside the dustbin, forcing it through this fan at the top. The fan spins around very quickly. It then creates electricity with a little dynamo in there. The electricity should light these bulbs. Let's see. Whoa! That worked. That didn't. Hey! I'm getting light! I'm getting light from waves! Way! Yes! Electrical power from waves. Not much electrical power, but it's definitely there.
But can we ever get more than a tiny flash from wave power? Well, yes.
I want to show you something that extracts millions of watts of electricity out of waves. But it's not here, it's up in Scotland.
The real obstacle to commercial wave power is designing a system that can withstand the massive ocean waves that smash into our coast. Ships have a hard enough time bobbing around on top of them, but to extract power from them, wave power machines have to find a way of absorbing that energy, and that usually destroys them. Built in Edinburgh, the Polaris system might just have solved that problem.
With wave power, survivability is everything. If you imagine a vessel like that side onto a big wave, it's going to get smashed to pieces. So what Polaris does is what a ship would do in a heavy sea. It turns itself nose on to the waves. Nose on gives it the minimum impact from the waves, but the whole purpose of it being out there is to collect the wave energy. How does it do that? Polaris is actually made up of 5 huge floating sections. Now imagine these are 2 of them. As the wave goes underneath, they rock up and rock back down again. And it's that movement that the power generation comes from. Now if you look here, between the sections are these huge pistons, and they get squeezed in and out with every wave. How that generates electricity, though, is all in here. Hi, Ross.
Hi, Jim.
So I guess this is the back end of one of those big pistons out there.
Yeah, this is where the energy actually comes from the wave-induced motion of the machine into the machine so we can make use of it. These are just like giant bicycle pumps pumping up a big bicycle tyre. So they suck in low-pressure fluid from these tanks here and then pushes it out at high pressure into storage accumulators.
And those accumulators are supposed to smooth the whole thing out, because otherwise it's like squirt, squirt, squirt.
Exactly, yeah. The waves deliver their energy in bursts, so we're collecting those spurts of energy and smoothing it out.
Can we have a look at the accumulators?
Yeah, sure. Just
Thank
here.
you. Oh, yes. Okay, so these are the accumulators.
Yeah, this is where we store energy between waves.
Do you mind if I pull a gun at this point?
Go ahead.
It's only because it strikes me that pretty much what you've got is like a water pistol. It's kind of like squeezing fluid out as each wave comes in, but what you want is a smooth, constant flow.
That's right.
It's the same problem I had with my little wave machine on the beach. The energy came in bursts. So what Polaris does is store up that energy it gets from each wave as high-pressure fluid, then releases it slowly to give a constant drive to its turbines.
These accumulators are like a large vessel, like a bucket. So it doesn't matter how spurty the incoming power is, as long as we can tap it out smoothly from the bottom, which is what these enable us to do.
Got it. And I guess this is where it all ends up.
That's right. The fluid from the high-pressure accumulator spins this electric generator to produce electricity.
The power is then fed along undersea cables to the shore station 5 miles away. The cleverest thing about Polaris, though, is that it can tune itself to the resonant frequency of the wave. Sophisticated computers on board adjust the angle between the sections into a slight zigzag. This means it gets as much movement, hence as much energy from the wave as it can.
How much electricity do you actually manage to produce?
Well, the whole machine is rated at 750 kilowatts, but on average over the year, we provide enough power for about 500 homes.
For about 5, so this big snake here can kind of run a village?
That's right, yes, on average over the year, yeah.
Cool.
Currently, Polaris is a prototype under test, and there are other wave power systems being tested too. Who knows? One day the most effective way of getting energy from the sun might be through the waves it generates.
So is this technology the future of wave power?
The thing is, wave power is such a difficult nut to crack. I mean, imagine the difference in power between a little wave and a huge wave.
Sure.
Nothing really survives out there. Now, the great thing about the Polaris machine is its survivability. It's able to produce power day in, day out in any conditions.
Good stuff.
Interesting. Actually, the Queen, on a recent visit to Canada, managed to charge her iPod just based on wave power alone. I'm sorry. Coming up now, it's Dr. Yan, and this week he's playing with ping pong balls. Say nothing, Jen.
So the challenge is how high can you blow this ping pong ball out of the top of this tube?
Okay.
Go on then, give it a try. Whee, not bad, yeah.
Well, I've lost it already.
Yeah, so that's about that much, isn't it? That one wasn't so good. Whee! We'll pick it up later. Oh, not bad, not bad. How do you think you'd do with something like that?
A bit better.
Yeah? It's weird, isn't it?
Yeah. Just blow it out.
Just blow it out, yeah. You really expect that the stream of air from your mouth would just like hit the bottom of the ball and blow it out, just like the tube, yeah?
Go for it, girl. You can't, it's impossible.
Isn't that because the air isn't as concentrated in one area?
Yeah, so it's interesting you say that. It's a bit like that. It's actually to do with air pressure and a much misunderstood idea which goes by the name of Bernoulli's principle. Bernoulli's principle says that the acceleration of stuff like air is always accompanied by a drop in pressure. But I'll show you with this funnel, and I'll use, just to make it clearer, without me having to sort of blow and so I can talk, I'll just use an air pump, which is basically just like me blowing, yeah? So it does go up a bit at first, but then all the air starts rushing around the side. And there's a lot of air that's coming out of my lungs or out of this tube. And to get all that airflow through that tiny little narrow gap between the ping pong ball and the side of the funnel, at the same rate as it's coming out of my lungs, it has to go a lot faster in just that spot. That means that this bit here has low air pressure. And because of the shape of the funnel, that low pressure bit is at the bottom of the ball. And so the bottom of the ball is being hit with much less force by the air than you might think. And that's enough for the air pressure out here to be hitting the top of the ball and holding it in place. And it's not just that, you can even use it against gravity. Watch this. You did it really well, actually.
Thank you.
You've got a nice constant airflow.
That's going to keep the boys entertained for years to come.
Genius, genius. I tell you what, that's your Christmas present.
If you send me one of those, I swear.
It'll be a nice one.
Next
It'll be
up,
nice.
in 1859, my hero, Charles Darwin, published his theory of evolution by natural selection. Now, even to this day, some people actually still contest the theory, often giving the eye as an excellent example of something far too complex and perfect to have evolved from scratch. Well, I'm on a mission to prove Darwin right. Eons ago, animals had to bump into things to know what they were. Imagine the benefits if they could develop an awareness of food before actually stumbling upon it, or of predators lurking nearby. Well, lucky for us, evolution has given us the perfect tool for this, the eye. But how on earth does something so incredibly complex actually evolve? Before I answer that, I've come to the Oxford Eye Hospital to find out how my own eye works.
The eye is very much like a camera. The light rays will come into the eye, they'll be focused by the lens, like the lens of a camera.
Yeah.
They'll go through the jelly of the eye and then they'll be focused onto the back of the eye, onto a structure known as the retina, which is lined by the photoreceptor cells, which is like the film of the camera.
Okay.
And the photoreceptor cells generate an electrical signal from the light energy. This electrical signal is then sent along through the optic nerve back into the brain.
And that's translated into the image that we actually see. The eye really is extraordinary, but can something so complex evolve in gradual stages? To find the answer, I've come to meet world-renowned evolutionary biologist Richard Dawkins. Richard, the eye is such a complex structure. I can understand why some people find it hard to believe it evolved out of nothing. Even Darwin commented on its complexity, didn't he?
Yes, Darwin said that it was impossible to imagine that it could have evolved by gradual degrees. But reason tells me that if there were a series of gradual improvements, then it would be easy for it to have evolved by natural selection. And you find all over the animal kingdom eyes in various stages of what look like stages of evolution.
And the great thing about this is that we've got examples of the intermediate stages of this evolution in modern-day animals. So, what would the first step be?
In here, for example, is Euglena, which is a single-celled organism, just has a little eye spot at the head end of the cell. And that eye spot is just sensitive to light, so it can't form an image, it can't see anything. All it can tell is whether it's light or dark, so that could be the first step.
Okay.
But if you imagine that you had a sheet of cells, each of which is sensitive to light. This has been painted with a substance that glows in ultraviolet. So and this is an ultraviolet light. And if we hold the ultraviolet light over, you can see it's sort of glowing.
Okay, so this demonstrates cells that are reacting to light.
Yes, that's just a flat sheet of cells, which
and you can't tell what direction
doesn't
the
tell
light
you
is
what
coming
direction.
from then.
But if you just gradually evolve a slight curve, turn it into a cup, light that's coming from that direction hits this side of the bent sheet of the cup. Whereas if the light's coming from over here, then the other side lights up. So you can tell what direction the light's coming from, and perhaps you could tell the direction that a predator's shadow is passing over.
This means that animals with cup eyes, like these planarian worms, have a huge evolutionary advantage over animals with just a flat eye. Then how do we progress from something that has a cup that can tell the direction of light to something that can actually form an image of what it's seeing?
Well, over evolutionary time, if you imagine that the cup gradually evolves to get deeper and deeper and deeper and close up the hole at the top, then you get a pinhole camera. Now, a pinhole camera is a pretty poor piece of work. It doesn't actually show you much of an image, but it does show you a crude image. You can actually see something. This is a pinhole camera here. In front is a little hole. There's a screen inside there.
Yeah.
Have a look.
Okay.
And if I now hold this in front of the pinhole.
Okay. Wow, yeah, no, I can see the A. It's not too bad. I mean, it's blurry, obviously, and it's upside down, but yeah, I can see it. And a perfect example of this next stage in the evolution of the eye can be seen in many aquariums. This is the mollusk Nautilus, a relative of the extinct ammonite, with an eye on each side of its head that acts like a pinhole camera, which means that these little fellas can see blurry images. This image might be good enough for Nautilus, but what if you wanted a bit more detail?
The solution to the problem, as anybody will tell you, is a lens. And a proper man-made lens is exactly shaped. It's a glass, refracts light.
How on earth does that come about in nature?
Well, to get a really good image, you do need a decently curved lens. But any old bit of gunge, which is transparent, will do if it's just approximately curved.
Okay.
I mean, this is just a polythene bag full of water, and it just naturally falls into a curved shape. Now, if I stick this bag of water...
Bring the bag forward a bit. There, perfect.
That's not what you might call a real lens. Think of that as just a blob of gunge in the cup eye.
But if this gunge or jelly hardened, it would form a proper lens and transmit a brighter, clearer image. And we can see an example of this back at the aquarium. Sea snails have a blob of jelly that acts like a very simple lens, so they can focus on an object even if that image is still a bit blurry. But it does mean they can make out food and predators.
Once you've got that, then because it works a bit better than nothing at all, you've got the raw material for natural selection to go to work and over generation after generation after generation, just each stage, just slight improvement in the curvature, slight improvement in the transparency, and you've got a steady ramp of improvement all the way up to a proper lens, such as you get in the vertebrate eye.
So really the eye is a brilliant example of how complex structures, and then obviously simpler ones, can evolve quickly and easily.
The eye is sort of legendarily complicated, and so if you can show that that evolved very easily and quickly over time, then all the more easy it would have been to evolve something simple.
What's even more incredible is that as the eye evolved over millions of years, wildly differing species like monkeys and mollusks seem to have developed the same solutions. And at the top of the mollusk evolutionary ladder is the octopus eye. It's got a proper lens, it can adjust its own exposure. In fact, its eye is pretty much like our own, except that it comes from a completely different evolutionary line.
Wow, you got to meet Richard Dawkins.
Nice. I know, and he signed My Selfish Gene.
Nice. Here's a question for you. How long does it take to get from nothing to a working eye?
Well, scientists have done a lot of modelling on this, and they reckon it only took about 400,000 generations to get from the simplest light-sensitive cell all the way to a fully functioning eye. So, given that this all started in simpler aquatic organisms that have very short life cycles, this means the eye would have evolved in less than 500,000 years, which may sound like a lot, but actually, in evolutionary terms, it's the blink of an eye. Do you like that?
I like what you did there. I saw what you did there.
Well, that's it for this week, but we will see you next week. Say goodbye, boys.
Bye.
Bye.